previous episodes, we examined the mainstream narrative of radiative forcing, its limitations, and the atmospheric window. We saw that radiative efficiency depends on atmospheric state, especially humidity. Now we turn to something more fundamental: water. Not just as a greenhouse gas, not just as vapor in the air, but as a thermodynamic regulator of planetary temperature. Before we discuss radiation further, we must understand the physics of water itself. Water has an exceptionally high specific heat capacity. This means it can absorb large amounts of energy with only a small change in temperature. Oceans cover about 71% of Earth's surface and contain the vast majority of the climate system's heat capacity. When energy enters the climate system, most of it does not immediately warm the air. It is stored in the oceans. This is called thermal inertia. Temperature does not respond instantly to radiative imbalance. It responds slowly because energy is being distributed into a massive reservoir. Without oceans, Earth's temperature would fluctuate far more dramatically. Water has another remarkable property. It changes physical states within the temperature range of Earth's climate. When ice melts, it absorbs energy without increasing temperature. When water evaporates, it absorbs energy, again without increasing temperature. This is called latent heat. Enormous amounts of energy can be absorbed or released during melting, freezing, evaporation, and condensation, while temperature remains nearly constant. It takes more than 5 times as much energy to evaporate water than to warm the same amount of water from 0 to 100 degrees Celsius, which is from 32 to 212 degrees Fahrenheit. This is not a minor correction. It is a dominant energy pathway. Consider Arctic sea ice. When additional energy enters the Arctic system, part of it goes into melting ice. Instead of rapidly increasing air temperature, energy is absorbed by the phase transition. As long as ice remains, part of the additional energy is diverted into melting. Once the ice area is substantially reduced, a larger fraction of incoming energy contributes directly to temperature increase. The same principle applies when climate cools. When polar regions receive less energy, liquid water freezes and releases latent heat. This released energy partially offsets the energy deficit, slowing the rate of temperature decrease while the phase transition is ongoing. This is a thermodynamic break. Not infinite, but real. To understand atmospheric moisture, we must distinguish between two concepts. Absolute humidity tells us how much water vapor is actually present in the air. The maximum amount the air can contain, called saturation humidity, strongly depends on temperature. Warmer air can hold significantly more water vapor. When temperature increases, saturation humidity increases. Saturation humidity tells how much water vapor air can hold. This is described by the Clausius-Clapeyron relationship. Saturation vapor pressure increases approximately exponentially with temperature. This means that as temperature rises, the atmosphere's capacity to contain water vapor increases significantly. Relative humidity is a ratio. It tells us how close the air is to saturation. In other words, this figure describes what percentage of absolute humidity is the actual amount of water vapor in the air. Relative humidity is the humidity that we meet in weather forecasts, and this is what desktop weather stations display. However, at cold temperatures, even 100% relative humidity corresponds to very little water vapor in the air. In warm climates, the air can hold much more moisture. Therefore, the radiative effect of water vapor is much stronger in those regions. Water vapor is therefore not constant. It scales with temperature. Water vapor is the most abundant greenhouse gas in Earth's atmosphere. Its absorption spectrum spans much of the infrared range, and as described in the previous part, it significantly overlaps with carbon dioxide. In humid air, outgoing radiation interacts strongly with water vapor. In dry air, the same radiation can escape more easily. If atmospheric humidity were significantly reduced, Certain additional infrared regions would become more transparent, particularly on the sides of Earth's radiation spectrum in the 5 to 8 micrometer and 18 to 25 micrometer ranges. In these conditions, much of Earth's infrared radiation outside the main carbon dioxide absorption band would encounter significantly less absorption, and much more energy would escape to space compared to humid conditions. Accordingly, if absolute humidity is very low, carbon dioxide plays a proportionally larger role in shaping the outgoing radiation spectrum. Therefore, it becomes relatively more influential in the climate of that region. Humidity is not just a detail, it modifies the radiative structure of the atmosphere. And unlike carbon dioxide, water vapor concentration can change rapidly and regionally. It is dynamic. Now consider 4 environments: the Moon, Antarctica, a dry desert, and a humid tropical rainforest. The Moon has no atmosphere and no water. There is no carbon dioxide or water vapor. Its temperature swings between extreme heat and extreme cold. During the day, temperature can change between -180 degrees Celsius and +130 degrees Celsius. In polar regions, there are no days for astronomical reasons. There are 6 months of daylight and 6 months of darkness. The temperatures in the inner regions, away from oceans, are more extreme. It can change between -20 degrees Celsius in summer and -60 degrees Celsius in winter. Here, atmospheric moisture is very low, and under these dry conditions, the relative contribution of carbon dioxide to the greenhouse effect becomes more significant. Deserts contain very little atmospheric moisture. Water vapor concentrations are low, although carbon dioxide is present in the same proportion as elsewhere on Earth. In the Sahara, the difference between daily minimum and maximum temperatures can even reach 38 degrees Celsius. Humid regions show much smaller daily temperature ranges. In tropical rainforests, the daily temperature fluctuations are very small, typically around 5 degrees Celsius. These regions are very humid. There's lots of water vapor in the air, contributing to a very strong greenhouse effect. If a planet has neither greenhouse gases nor liquid water, surface temperature variations can become extreme, creating a hostile environment for life as we know it. In very dry regions on Earth, greenhouse gases, primarily carbon dioxide, play a relatively larger role in limiting radiative heat loss, thereby moderating temperature swings. Even though temperatures can still be harsh, life remains possible. Where water is abundant, its high heat capacity, phase changes, and atmospheric moisture significantly reduce temperature extremes. These more stable conditions are generally more favorable for complex life. What does water do to achieve this? It stores energy. It transports energy. It buffers energy. We have now seen that water stores heat in the oceans, absorbs energy during phase changes, buffers temperature rise, and reshapes atmospheric radiation through humidity. But water does more than storing energy. It moves energy. Vertically, horizontally, continuously. If water governs how energy is stored and moved, then climate change cannot be understood by radiation alone. In the next part, we explore how moisture transport, latent heat, and radiation interact, and how this dynamic system regulates planetary temperature. In the following part, the role of water will be explored even further to see how its dynamic processes affect climate change, while strictly remaining within the boundaries of science and the laws of nature. If you liked this part, don't forget to like the video and subscribe to the channel so you don't miss the next part and other exciting videos being released in the future.